Welcome, everyone, and thank you for having me and for attending this session. My name is Sergio Maurenzi. I am the responsible and the founder and the CEO of Peperina Software, a cloud-native software engineer firm located in Argentina. Well, today I will present a project, a modernization project about a tax information system in the public sector where we use a reactive architecture approach. This is the agenda for the presentation. Because perhaps we have no time, the Q&A session will be outside. Well, a little bit of context about the project. Córdoba is the second most populous province of Argentina with almost 3.7 million inhabitants. And the government agency called DGR, or Dirección General de Rentas, and Collector UT is a private health company. They are responsible for collecting the taxes for the province, for the states. The taxes are basically fees related to properties, real estate, vehicles, boats, and business income. In 2015, the agency started to move the statement of these taxes, to their website. And they start to have many problems of basically availability, performance. And that's why in 2019, they decide and ask or request the IT department to think a different solution, to think out of the box, a different solution for providing this service to the taxpayers. At that moment, they decide one key business objective: allow the taxpayer to search and pay their statement always. And the last word, always, is very strong, you know? The tax agency required to think this solution, as I mentioned, out of the box. Because we don't believe in a big bang project, migration project of the legacy system. That's the reason that we provide, or we think in a key technology objective, that is decouple the functionality of search and payment from the legacy system as much as possible. Well, these were the non-functional requirements of the project. I think they explain themselves, but basically the solution must be responsive, resilient, always on, performant, and have the capability of track every transaction because it's money of the citizens. This out-of-the-box thinking was the origin of the name of the project, Copernicus. We propose and design from the ground up a solution that is a cloud-native, reactive, and microservices, and also event-driven architecture. And this is the high-level architecture of the system. Basically, it is a pipeline that ingests and processes the changes that we call them events, because they are produced in the legacy system every time an important change happens in the business domain. Of course, are you seeing? Yes, it's good. It's seeing good the image, because we have a problem with the interface. And we have also a feedback loop from the consumer apps for the commands and queries of the repository. enter into more detail. The pipeline starts with the data source, with the CDC or change data capture. Every time an entity state from the data source is changed in this database, that is an update, an insert, or a delete, a DB trigger copies this record of the DB, of the table, in another table called outbox. Then the pipeline continues with the ETL. In this process, there is some transformation, enrichment of the data. There are many processors ingesting these records. And then part of this data pass through a new component that is a business rule layer. This is a business rule engine that processes certain events, not all events, certain events, to classify the debt of the taxpayer, which is defined by more than 45 business rules. Yes, in our country, we have many creative with the definition and exception of the debt. In this case, the business area can change the rules represented as rows in a DMN file. DMN is decision modeling notation. It's a standard of business rules. And then the next stage is the messaging system. And as the name suggests, the main characteristic of this messaging system is it is an event card state transfer pattern. And that means that the events are stateful events. And that's why we can't lose any of them. Then the consumer of this stateful event is the ACA platform, or ACA cluster, who build the private replica by storing the state in the actor model. This is a really short period of time that the data is lagging behind from the data source, and that's why it is eventual consistency, no strong consistency. The actor model for the business logic is the core application, which is based on distributed and concurrent processing. Then we choose event-sourced entities because the NFR that I mentioned before, that is related to the old log of every transaction. Also, we have a CQRS. We provide the read data model to allow to be exposed through APIs by the BFF to the consumer apps. The BFF, the back for front end. Well, and this is the technology stack for every component through the pipeline. Apache NiFi for the ETL, rules for the business rule engine, Kafka, the messaging system, ACA actor model, programming in Scala, and the two repositories, write side and read side, are running into a NoSQL database, Cassandra database, and the consumer-facing application that are in the front for accepting the query and commands are Node.js applications. All of the components or the architecture are cluster aware. And in the case of Kafka, Scala, or all of this, the ACA, Kafka, and the Node.js application are living in the Kubernetes cluster. Before starting to code, we spent several workshops, days, with the business and IT area, trying to understand the process, the business process. We use event storming for trying to capture the whole information about this process. And then we have different sessions to modeling the data. And here there is a simplified view of this relationship between the main entities that are in this kind of system. The person or taxpayer we represent here with, well, the name is sujeto in Spanish, is represent the taxpayer. The assets of the person are called objeto in Spanish, and the liability or obligations are related. These three entities are very related, and that's why we are putting in an aggregate. For example, if you have a message of paying a liability, the message entered by the aggregate route and is routed to the corresponding liability to update, in this case, the balance. This also update her parent, or in this case, the objeto or asset, and then update the balance of the person, sujeto. And the last step is to emit an event. This is a simplified workflow of what happened between these entities. Well, during the project, we have many challenges. This photo is from Cordova mountains. I love mountains, but guess what? This guy is not me. I still prefer technical challenge. Well, during the execution of the project, well, as I mentioned, many problems, but mainly, well, here we will talk about throughput, observability, and schema evolution. One of the requirements of the project was to process the full entity states previous to the beginning of the next year, because every year the tax agency generates the liability for a full year for every taxpayer. This is a batch process. We call it initialization. It includes almost 100 million of new records to update during the weekend window. On the other hand, on the ongoing process, every day we process 2 to 8 million of records or events per day. When we talk about improve the throughput into the pipeline, we have many places to tune in or improve it. For this presentation, I just talk about this. One of these improvements is related to the messaging processing stage. I think that you already know about ACA, but I don't know if are you familiar with ACA streams here? Yeah. Well, ACA stream, just a little, is a module built in top of ACA actor to make the ingestion and processing of a stream easy. And the Alpaca project is a kind of library that brings us a bunch of connectors to integrate various systems in ACA streams. Here we will talk about Alpaca, only the Kafka connector. So here is the basic ACA stream pipeline. You need at least a source and a sink. Obviously, a source has an outlet, a sink has an inlet. And then you have an arbitrary number of flows in between. Message flow downstream from the source to the sink, but you also have the other channel going to the upstream. This is for back pressure. In Kafka, the main level of parallelism is the number of partitions in a topic. Here we have almost 90 topics in this project, one for each entity. And also we have topics for retry, processing certain events, error handling, and prioritization. Each partition is sharded by the entity ID. As we will see later, it is possible to expand the number of consumer instances to keep reading data from the same topic in parallel. A consumer subscribes to Kafka topic and pass the message into the Akka stream. In Akka streams, the Kafka consumer is also named source. Well, we have two approaches for doing this. The first one was approach was about the consumer Kafka transaction. Why? Because Kafka transaction allowed exactly once processing of message. Messages are consumed, transformed, and produced to another Kafka topic in one atomic operation. And all messages, including a transaction, will be successfully written, or none of them will be. This is the core of Kafka transaction. And according to our first test, it really worked well. But the problem arose when we put many events in the pipeline, when we increased the number of messages. We changed many settings. The number of partition, quantity of brokers, the number of Akka cluster nodes, the processing power of this node, but it changed slightly. We realized that we have a bottleneck in another area, in another component. Well, the first issue was related to the latency when building transactional pipeline that span more than an entity update. That is in the specification or in the talks that Sean Glove, for example, talk about this issue, the latency between the components in a transaction. But the most important, we discover, that is also in the documentation, is that this kind of consumer is not partition aware. And that means that if it cannot manage each partition in parallel, and that's why there is only one consumer for the 90 partition. And that's why we tried with the second consumer, a committable partition as source configuration. This config uses at least one semantics, different. The source uses a single Kafka consumer internally, but the committing works with partition. That means that it's partition aware. The at least one processing means that if the broker does not receive confirmation that the event is consumed successfully, the broker will resend the event. While this ensures that the event is get processed, it also means that it can happen multiple times. And we solved this problem introducing an idempotency. With this configuration, we can technically size our Kafka consumer with the number of partitions and the same consumer group run in parallel to achieve high throughput and high rate of data ingestion. It's like the slide show, like one consumer for each partition. Well, here's the code example of our consumer-made processor. I will explain briefly. The committable partition source method supports tracking automatic partition assignment from Kafka. When a topic partition is assigned to a consumer, this source will emit a tuple with the assigning topic partition and a corresponding source. And when a topic partition is revoked, the corresponding source completes. Here we can identify two map async operators. The map async operators, if you remember, allow us to process the flow in different actors, separating the boundaries and allowing us to execute the flow in parallel. It also important to remark that this prioritization of event is done in order. We have another method, map async and order, but in this case we use order because it's necessary for the events that are stateful. The first map async that is in the code is the source of each partition and has as prioritization parameter the number of partitions. And the second map async is the operator to process the message inside this partition. Here we use consumer parallelism environment variable to increase the parallel tasks to achieve a better throughput, but we couldn't achieve these better results with this increasing this parameter. The application turned unstable when we increased this parameter more than 5. Continuing with the code, we have the mapping of error in processing the message. We have two kinds of errors. One is related to the timeouts into the pipeline, because, for example, the database is one issue, for example. In this case, the queue for trying to retry this event, we implement this way. And the other one is normally related to serialization issues when we produce, in this case, message for another topic is for error topics. Here we can see the case for successful processing, which produce messaging into the corresponding success topic. At the end of this code, you can see also the sync method and the stream materialization or the running of the graph. Well, the next challenge is talk about observability. Of course, we have no time in this presentation to show you about every tool, every dashboard or graph. It's just a glimpse. But as you know, in distributed system, data and application observability is essential. Because the message that flow in the pipeline are events that represent some state changes that are important from the legacy application, the source of truth in this case, we need to ensure that we have no data loss. Every stage in the pipeline must be observable. We need metrics, log and traces, all of them. To look for the trace on each event, we use one unique identifier that we define for the CDC. We call EVID, which includes the timestamp when the trigger activate and a sequence number from the source database. In this presentation, again, we will focus on the observability just in main components of the message system and the business logic. And this is a slide, we are showing control center from Confluent Platform, and we can see the consumer lag of message from one of the topics. We see the total number of message behind and by partition. And also you can see the bar in the middle. Each bubble represents a partition and a position represents the number of messages behind. Because this tool shows the message consumption in live mode, we could discover the latency issue with the transactional consumer that I mentioned before. Because we saw how the consumer processed one partition at a time. We can see this movement one partition at a time. But when we change the consumer incommittable partition, we could see how the processing of all the topics are in parallel. Here we can see Kafka UI, an open source tool to manage or to show the message content through the Kafka. And here you can see the EVID that is remarked. It contains a timestamp, and we can compare the timestamp that was generated by the database and what it enters into the Kafka topic. And then we can see if we have any luck there. Fortunately, Lightbend provides several dashboards to help us to observe and monitor the behavior of the actor system in terms of throughput, latency, and consumption. This is one of them, of actors. And we have another about ACA streams, number of strips running, throughput, latency. I will starting to move forward, sorry. Another useful tool to capture the trace between the components inside the application, open tracing and zipkin. And of course, we define our own dashboard with Cinnamon and Camon. We use these libraries to include our metrics of our application. Next and last challenge present here is schema evolution. Working with event sourcing system, we discover some issues and challenges. The first one is related to the number of read events for recovery operation. Every time we need to recover the state of an entity, the persistent library reads every event from the beginning and replay them to compose the state. The problem with entities related as an aggregate is the number of events that they produce. For instance, when you have a tree like this, the parent sums the events of all of the children, all of the tree. In this example, it's just 5, but we have a big family. We have thousands of events running of grandchild or child or children. Because this is a common issue in event sourcing, ACA persistent library brings us a solution called snapshots. You can define, for instance, that after n events, you can take a snapshot of the state, and with this feature, you don't need to read all the events from the beginning. You just read the latest snapshot and the following events. This solution reduces drastically the response time on recovery of the state, but introduces another issue or challenge. The schema evolution is about changing the structure of the message according to the life cycle of this application. The snapshot we use in ACA Stream are not compatible with the library we use for serialization. We use Cryo library. We tried to change the library for Jackson, but the performance was worse. In the next slide, we are going to explain how we solved this issue. First of all, well, we have the snapshot of event of one of the entities, in this case, the person. Each snapshot contains the state of the entity and other fields that compose what we call a register. This register could include, for example, in this example, 3 fields, a type, address, and email. Now, if you want to add a 4th field, for example, the phone number, if we change the definition of the schema, when we recover the state from the snapshot, it fails because the snapshot doesn't know anything about this field. What we did here is to create a new case class at the application level to manage this like a new version of the schema. And when we read the schema, we compare with the different versions. And, well, these are the 2 case classes. The version 1, called Sujeto3, contains the all register. The version 2, called Sujeto3.2, is the one that contains the new field. And take into account that in our case, we have optional fields into the register. And that is why it's possible to evolve this register. This is the code where we do the schema transformation. ACA persistent support event sourcing with persistent actor. The behavior of persistent actor is defined by implementing receive recover and receive command. And here we override the method to change the behavior. The persistent actor receive recover defines how the state is updated during the recovery by handing event and a snapshot offer message. And here's the way we compare the snapshot with the corresponding schema, version 1 or 2. And in the case it is the old version, the snapshot is copied and updated. Well, final slides. Since the start of the project in 2019, the engineering team had many challenges and learnings. The rollout in production starting in 2021, last year, mid last year. The system went live with the initialization process and immediately starting to ongoing the process ingesting of all the events from the source system. But in terms of use, from the consumer point of view, a blockchain-based digital wallet, it was the first consumer, just started to use the data of our platform in a live way. This was part of our strategy to allow to tune in the platform. But then in the second half of this year, the system started to be integrated with different other platforms and systems, IVRs, website, new revenue system, etc. This platform is considered the glue between the legacy system and the new customer-facing systems. We are continuing developing new features, business features, like a discount module that is by nature reactive, need to be reactive. And of course, we continue to evolving and tuning the platform, especially increasing the performance of data processing and robustness of the events in the pipeline. Well, key takeaways. There is one universal truth. All things that can fail will fail, you know. It's not matter of if, but it's matter of when. If a single consumer fails, that isn't accounted for in the design state, replicas can divert permanently. That's why do not underestimate the complexity of maintaining a consistent state across microservices in a high availability environment at a scale. The second key lesson is about restriction and non-functional requirements. Review carefully for non-functional requirements that could change your architecture decisions. For example, the security audit logs the business part never then asked to show this part. We choose event sourcing for this. The third key lesson is about the resilience and responsiveness. As Hugh mentioned today in the morning, with these asynchronous and decoupled components, we could see how the system reacts to failures, like application nodes going down or issue with the network or with the database, without disrupting the service. Because, in one case, they activate the circuit breaker or a sprint break resolver, other part of the platform. This is really amazing. In conventional system, if you have an issue like this, the application becomes unavailable. In any case, the observability is essential, as I mentioned before, in distributed system. Okay, as you already heard, working with distributed system is hard, but worth it. At the end, we have more resilient and robust system, and our taxpayer and citizen deserve it. Thank you very much.